Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Imagine, one moment you're living your everyday life, birds chirping, cars driving by, children laughing in the park. Then, with no warning, the sky suddenly flashes, not with thunder or lightning, not with fire or sound, but with a silent, invisible beam of energy so intense that it pierces Earth's atmosphere like a blade through paper. You don't feel anything, not at first. But within hours, strange things begin to happen. Satellites go dead, communications fall silent, the protective ozone layer begins to shred apart, atom by atom. Days later, ultraviolet radiation from the sun scorches the surface. Crops fail, skin burns, DNA mutates. It was no war, no asteroid, no solar flare. It was a gamma-ray burst, an invisible assassin from the depths of the cosmos, so powerful it could end civilization in a heartbeat. Gamma ray bursts, or GRBs, are the most violent explosions in the known universe. They are cosmic events of such unimaginable energy that they challenge our very understanding of physics. For decades, even scientists didn't know they existed. When they were first detected in the late 1960s by the Vela satellites designed by the United States to catch cheating during nuclear test bans, analysts thought they might be secret Soviet weapons. But these bursts weren't coming from Earth, or even from the solar system. They were coming from deep space, from far beyond our Milky Way, and they were like nothing anyone had ever seen before. These bursts are flashes of extremely energetic gamma rays, the highest energy form of light, released during catastrophic cosmic events. Some last mere milliseconds, others can last several minutes, but in that short window, they can unleash more energy than all the stars in the galaxy combined. Think about that for a moment. Our sun, a relatively stable yellow dwarf, will shine for 10 billion years. A single gamma-ray burst can release more energy in just 10 seconds than our sun will across its entire lifetime. That's not science fiction. That's scientific observation, measured and confirmed using high-energy space telescopes like Fermi, Swift, and Beppo-Sachs. But where do these deadly flashes come from? Gamma-ray bursts are created in some of the most extreme environments imaginable. The two most common sources are the deaths of massive stars, hypernovae, and the mergers of ultra-dense, neutron stars. In both cases, we're talking about the endgame of stellar evolution, where the universe's most massive and compact objects either explode or collide. When a massive star, perhaps 20 or 30 times the mass of our sun, exhausts its nuclear fuel, gravity takes over. The star collapses inward, triggering a titanic explosion called a supernova. But in some rare cases, the collapse is so violent that it forms a black hole, and out of its poles, through complex magnetic interactions and relativistic physics, emerges a tightly focused jet of gamma rays. These beams are so concentrated that they travel across billions of light years and still reach Earth's detectors. When astronomers pinpointed the origin of GRBs, they discovered that some of them occurred when entire stars died, others when two dead stars, neutron stars, smashed into each other, producing gravitational waves, black holes, and gamma radiation all in one final cataclysmic act. These are not rare events in a universal timescale. Somewhere in the observable universe, a gamma-ray burst occurs approximately once every day. But most are so far away they pose no threat. The danger lies in one rare possibility, that one might occur in our galactic neighborhood, and that its deadly beam is pointed directly at us. Now, Earth is protected by a fragile bubble of gases called the atmosphere, and within that, the ozone layer plays a vital role. It blocks harmful ultraviolet radiation from the sun, making life on land possible. But a sufficiently close gamma-ray burst could tear that protective layer apart. If one were to occur within about 10,000 light-years of Earth, the incoming gamma rays could trigger atmospheric chemistry that breaks apart ozone molecules. Within weeks, our surface would be exposed to deadly levels of ultraviolet light. It would start subtly, an increase in skin cancers, crop damage, oceanic algae, die-offs. But over months, ecosystems would collapse. Without ozone, the very foundation of Earth's food web, from phytoplankton to apex predators, would begin to unravel. There's even evidence that this may have happened before. Around 440 million years ago, during the late Ordovician period, the second largest extinction event in Earth's history wiped out approximately 85% of marine species. One theory suggests that a gamma-ray burst triggered a cascade of climate shifts and ecological collapse. While we can't travel back in time to confirm it, computer models show that such a burst could account for the geological and biological clues we've found from that era. It's a chilling thought that life on Earth may have already been scarred by a celestial sniper. Some might ask, if these events are so rare, why worry? The truth is that rare doesn't mean never. Our galaxy, the Milky Way, is over 100,000 light-years across and contains over 100 billion stars. Statistically, a gamma-ray burst capable of damaging Earth might occur once every few hundred million years. But that's an average. The universe doesn't run on schedules. It's entirely possible that a massive star close enough to Earth is already nearing its death. Stars like WR104, a massive Wolf-Rayet star located about 7,500 light-years from Earth, have drawn attention from scientists. While WR104 isn't confirmed to be pointing a gamma-ray burst jet at us, its orientation and mass raise legitimate questions. If it were to go supernova and produce a GRB, and if Earth were in the path, we'd have no warning. The gamma rays would arrive before the light from the explosion did. The damage would already be done before we even knew something happened. And that's what makes gamma ray bursts so terrifying. There's no defense, no escape, no shelter. Gamma rays pass through everything but the densest materials, and at those energies, even lead shielding or thick rock offer little protection. Entire planetary atmospheres like ours would be the only real line of defense, and once that's gone, we're exposed to a hostile universe, unfiltered and unforgiving. Yet in all this terror, there's a strange beauty. Gamma-ray bursts are not just death. They are transformation. They seed galaxies with heavy elements. They help us study the early universe. They allow us to see across vast cosmic distances. The light from a single gamma-ray burst, like GRB 090423, has traveled over 13 billion years to reach us, meaning it occurred when the universe was less than 500 million years old. That's before Earth even existed. These cosmic events are time capsules, explosions so luminous that they become beacons from the infancy of the cosmos. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the deep, mysterious forces that shape our universe, hit that subscribe button. It's free, and it helps us grow a community of curious minds ready to face the cosmos together. To truly grasp the terrifying beauty of a gamma-ray burst, we have to dive deeper into the heart of dying stars, colliding remnants, and the exotic machinery of the cosmos. Imagine a star so massive that it dwarfs our sun, perhaps 25 to 100 times its mass. For millions of years, this giant burns furiously, fusing hydrogen into helium, then helium into heavier elements, climbing the periodic table step by step, carbon, oxygen, neon, silicon, all the way to iron. But iron is the end of the line. Fusing iron doesn't release energy, it absorbs it. And the moment a star reaches that stage, the balance between gravity pulling in and fusion pushing out collapses. The core caves in, and what happens next is nothing short of cataclysmic. In less than a second, the core of the star implodes under its own gravity. Temperatures skyrocket to billions of degrees. Electrons are crushed into protons, forming neutrons. Neutrinos, ghostly particles, burst out in unimaginable quantities, and then, in a final, desperate recoil, the outer layers of the star explode, outward in a supernova. But in rare cases, maybe 1 in 1,000, this isn't the end. If the conditions are just right, and the star is rotating fast enough with an intense magnetic field, it can form something far more extreme, a black hole. And here's where things get otherworldly. As the black hole forms, material from the collapsing star funnels into it at near light speed, creating an accretion disk, an inferno of plasma spiraling into oblivion. Magnetic fields twist into violent coils. and out of the poles of this newborn black hole erupt twin jets of energy, so focused and so fast they punch through the star's outer layers and burst into space. Those jets are gamma-ray bursts. The physics behind these jets is still being studied, but we know they involve relativistic particles, matter moving at nearly the speed of light, and magnetic fields billions of times stronger than Earth's. These jets are collimated, meaning they don't spread out like a flashlight beam. They're more like high-powered lasers, thin, precise, and unimaginably powerful. If you're in the path of that jet, it's like staring down the barrel of the universe's deadliest weapon. Another type of gamma-ray burst comes not from dying stars, but from the collision of neutron stars, what scientists call short-duration gamma-ray bursts. Neutron stars are the remnants of supernovae themselves, dead stars crushed into city-sized objects with masses greater than the Sun. A teaspoon of neutron star material would weigh around 1 billion tons. Now imagine 2 of these monsters orbiting each other, spiraling closer and closer over millions of years due to gravitational radiation. When they finally touch, they merge in a titanic explosion, releasing gravitational waves, forming a black hole, and yes, blasting out a short but deadly gamma-ray burst. In 2017, humanity witnessed this firsthand. The event, named GW170817, marked the first time we observed both gravitational waves and light from the same cosmic collision. It was a neutron star merger, and it confirmed what theorists had long suspected. Short gamma-ray bursts are real, and they are linked to these violent mergers. The resulting burst was relatively weak by the time it reached Earth, but it was a wake-up call. These things happen, and we can see them. But seeing them doesn't mean we can stop them. The real danger is that we don't know where the next one will be or when. Because these bursts are so directional, we might only detect a small fraction. For every burst we spot, there could be hundreds more that fire off in directions we can't see. And that brings us to one of the most unsettling truths in astrophysics. If a gamma-ray burst were heading straight for Earth, we probably wouldn't know until it hit. Unlike other cosmic threats, asteroids, solar storms, even supernovae, gamma-ray bursts travel at the speed of light. There's no shockwave, no approaching light flare. The moment our satellites detect it, it's already here. And if it's strong enough, it could start damaging our upper atmosphere within seconds. But what does damage really mean in this context? Let's talk about the ozone layer, the invisible shield that absorbs most of the sun's harmful ultraviolet radiation. A gamma-ray burst doesn't hit the ground. Instead, its high-energy photons slam into nitrogen and oxygen molecules in the stratosphere. This breaks apart molecular bonds, forming reactive nitrogen oxides, compounds that catalyze the destruction of ozone. Think of it like pouring acid onto a delicate fabric. Except that fabric is our planet's only real protection from sterilizing ultraviolet light. Computer simulations have shown that a gamma-ray burst from about 6,000 light-years away could destroy up to 50% of the ozone layer globally. Closer bursts could eliminate over 90%. That's not just an environmental issue, it's an existential threat. With no ozone, every living organism on land would be exposed to levels of UV radiation far beyond survivable thresholds. Crops would wither. Marine plankton, the base of the oceanic food chain, would die off en masse. Mass extinctions would follow. And here's the cruel twist. All of it could unfold without a single visible sign in the sky. No warning, no fireball. Just a quiet rearrangement of atmospheric chemistry, and then the slow unraveling of ecosystems. What's more, GRBs could also affect climate. By altering the composition of the atmosphere, they could reduce sunlight reaching the surface, triggering what's known as a cosmic winter. In this scenario, temperatures drop, weather patterns shift, and precipitation decreases. The world becomes colder, darker, and more hostile. We often think of global warming as the great environmental challenge, but imagine the opposite. A sudden plunge into an ice age, triggered not by Earth, but by the death throes of a distant star. Scientists have proposed using ice core samples, fossil records, and ancient sediments to look for signs of past GRBS. Some anomalies, like sudden increases in certain isotopes, might hint at cosmic radiation events, but the evidence is circumstantial and the signals are subtle. What we know for sure is that these events are part of the universe's natural cycle. Stars are born, they shine, they die, and sometimes in their death, they scream. And we're left to wonder, how many times has life elsewhere in the galaxy been wiped out by a silent gamma flash? If intelligent civilizations exist, or once existed, they too may have faced this unpredictable terror. It raises the unsettling possibility that gamma-ray bursts could be part of the answer to the Fermi Paradox, the mystery of why we haven't heard from alien civilizations. Maybe the universe is teeming with life, and maybe the most dangerous place for life to exist is near a massive dying star. And if that's true, what does it say about us? Now that we understand the terrifying potential of gamma-ray bursts, those cosmic time bombs that lie dormant in the universe, waiting for the right moment to explode, it's time to confront a crucial question. How likely is it that Earth will be caught in the crosshairs of one of these deadly events? To answer that, we need to dive into the unpredictable nature of our galaxy, the Milky Way, and explore the distances, the directions, and the ticking clocks of the stars. As we've seen, gamma-ray bursts can happen anywhere, but they're destructive. Power depends heavily on proximity. Distance is the great equalizer in space. The farther away a burst occurs, the less likely it is to have any significant impact. A gamma-ray burst that occurs 10,000 light-years away from Earth would be far less dangerous than one that occurs just a few hundred light-years away. But how close is too close? To put it into perspective, the closest known gamma-ray burst occurred in the constellation of Centaurus, around 450 million light-years away. That was far enough that we didn't see any direct effects. But here's the kicker. Astronomers have recently identified stars that are much closer, some as close as a mere few thousand light-years, and that's where the danger lies. The Milky Way is home to hundreds of billions of stars, and many of them are in their late stages of life, ripe for collapse into black holes or supernovae. These stars may be waiting to unleash their energy in the form of gamma-ray bursts, and Earth could be in their line of fire. But the truth is, we have no way of predicting when one of these stars will go supernova, or worse, form a gamma-ray burst-producing black hole. So let's explore a key player in this cosmic game: the massive, volatile stars known as Wolf-Rayet stars. These stars are in the final stages of their evolution and are known to be prime candidates for generating gamma-ray bursts. They're not just big, they're extreme. Wolf-Rayet stars can have masses anywhere from 20 to 40 times that of our Sun, and they burn through their fuel at an astonishing rate. In fact, they are so hot and so luminous that they shed their outer layers in a violent wind, leaving behind only a dense, highly unstable core. These stars burn through their hydrogen fuel so quickly that they have a much shorter lifespan than smaller stars, only lasting a few million years. When their time comes, the result is nothing short of cataclysmic. BUR-104, located about 7,500 light-years away in the constellation Sagittarius, is one of the most famous examples of a potential gamma-ray burst progenitor. This star has been studied extensively because of its peculiar characteristics. It's rotating rapidly, and the tilt of its axis is aligned in such a way that if it were to collapse into a black hole, the jet would be pointed directly at us. That's right, WR-104's gamma-ray burst could in theory strike Earth. The idea is so unsettling that some astronomers have even coined it the Doomsday Star, though it's important to note that the star is not close enough to pose an immediate threat. Still, its existence serves as a stark reminder of the randomness of cosmic violence. For the record, this star isn't expected to go supernova anytime soon, but it's a reminder that there are ticking time bombs scattered throughout our galaxy, each one a potential gamma-ray burst waiting to happen. While WR-104 is an intriguing case, there are many other stars that pose similar risks. The Milky Way is littered with dying stars, and many of them are located far closer to Earth than WR-104. But these stars aren't just ticking time bombs, they're part of a larger cosmic ecosystem. When one of these stars dies, the energy it releases has profound consequences not just for Earth, but for the entire galaxy. This is the universe's way of recycling matter. The explosions from these stars create the heavy elements that make up planets, moons, and even life itself. Without supernovae and gamma-ray bursts, we wouldn't have the elements necessary for life. Elements like carbon, oxygen, and iron. The very atoms that make up our bodies were once forged in the heart of dying stars. But while we owe our existence to these explosions, it's also true that their destructive potential could mean the end of life as we know it. And as we peer into the depths of the universe, we see a startling truth. Gamma-ray bursts are more common than we'd like to think. Every day, somewhere in the vastness of space, a star is dying. And although the majority of these bursts are too far away to affect us, it's impossible to ignore the fact that our galaxy is a volatile, ever-changing place. The challenge for astronomers is that gamma-ray bursts are nearly impossible to predict. Unlike supernovae, which are somewhat easier to detect as stars begin to show signs of instability, gamma-ray bursts occur when a star collapses or two neutron. Stars collide, but only the jet of gamma rays is visible to us. The rest of the event, the supernova or neutron star merger, may occur in a matter of seconds, but it's the gamma rays themselves that travel outward, across the fabric of space-time. Because of the directionality of the burst, we could have only a few seconds of warning before the destructive energy hits. Even with the most advanced telescopes in the world, we'd be unable to intercept or shield ourselves from that deadly burst. However, there is a silver lining. Gamma-ray bursts do not last long. The bursts themselves typically last from a few milliseconds to a few minutes, but their effects on Earth's atmosphere can linger for weeks or even months, depending on the intensity and proximity of the burst. The burst's energy is so concentrated that it would be almost impossible to escape its reach. But even if we can't prevent or avoid a gamma-ray burst, there may be some hope for survival if we have enough warning. If we detect a burst far enough in advance, it's possible that certain measures, like protecting crops, increasing atmospheric shielding, and preparing for long-term environmental effects, could mitigate the worst effects of the event. Yet, all of this remains in the realm of theory. The idea that we might someday witness a gamma-ray burst up close is both terrifying and fascinating. These bursts are not just stellar phenomena, they are a reminder of how fragile life on Earth truly is. Even though we've made incredible strides in understanding the cosmos, there's still so much about these explosive events that we don't know. The future of gamma-ray bursts remains uncertain, as does the future of humanity. But one thing is clear. These bursts are a part of the natural order of the universe. They are the ultimate demonstration of the raw power of space, a power so overwhelming that it can end civilization as we know it in the blink of an eye. As we stare into the vastness of the universe, we are reminded of just how little control we have over the forces at play. The only thing we can truly do is continue exploring, learning, and preparing for the unexpected. Because in the end, we are all travelers on this cosmic journey, and gamma-ray bursts are just one of the many mysteries waiting to be uncovered. As we step deeper into the abyss of the universe's most dangerous phenomena, it's important to reflect on how humanity has dealt with such cosmic threats throughout history. From the ancient myths of celestial omens to the modern scientific understanding of space, our relationship with the cosmos has always been one of awe and fear. But now, we are no longer passive observers. We've learned to send probes into deep space. We've mapped the stars and we've even unlocked the fundamental forces that govern the universe. Yet in the case of gamma-ray bursts, we find ourselves helpless. We may understand the physics behind them, but the truth remains. There is nothing we can do to stop one. At least not yet. The first step in understanding how we might protect ourselves from such a cosmic event is to recognize the problem. Gamma-ray bursts are both sudden and unpredictable. These bursts don't announce themselves with ominous warnings. There's no countdown, no bright flash in the sky to alert us to an incoming threat. The gamma rays themselves travel at the speed of light, and by the time we detect them, they have already done their damage. Unlike a solar flare, which can be forecasted to some extent, a gamma-ray burst is a one-off event, happening only once in a while, but with the potential to be devastating when it does. So, what can we do? Is there any hope for survival? For years, scientists have been brainstorming ideas, not necessarily to stop a gamma-ray burst from occurring, but to shield ourselves from its destructive energy. The concept of atmospheric shielding has been one of the most discussed, but it's not as simple as just covering the Earth with a giant protective shield. We are talking about an astronomical amount of energy here. Gamma rays so powerful, they can penetrate light years of space without losing any of their intensity. It would take an incredibly dense material to stop them, something far beyond what we currently have access to. Even the most advanced technologies would struggle to deflect or absorb the sheer power of a gamma-ray burst. Instead, the focus has turned to preparation. What if, instead of trying to stop the burst, we learned how to adapt to the aftermath? A gamma-ray burst would primarily affect the upper atmosphere, so one key aspect of survival would be shielding our vital systems from the immediate damage. The ozone layer, our primary defense against ultraviolet radiation, would be decimated by the burst's high-energy photons, and with it, life on Earth would be exposed to a host of environmental challenges: intensified UV radiation, crop failure, massive disruptions to ecosystems. If the burst were strong enough, it could also trigger a global cooling event, known as a cosmic winter, which could reduce sunlight and lower global temperatures for an extended period. If humanity is to survive such a cataclysm, our ability to adapt will be our most valuable resource. Some researchers have speculated that we might be able to shield critical agricultural areas, or even genetically engineer crops to withstand higher levels of UV radiation. Others have looked into the possibility of creating underground shelters, complete with self-sustaining ecosystems, to protect human life during the aftermath of a gamma-ray burst. Yet none of these solutions are foolproof. We are dealing with a phenomenon so vast and powerful that even with the best preparation, the odds of survival are uncertain. We may be able to mitigate the damage, but there's no guarantee that life as we know it would survive intact. But here's the thing. The threat of a gamma-ray burst is still highly unlikely. The chances of one occurring close enough to Earth to cause significant damage are very small. Astronomers estimate that a gamma-ray burst strong enough to threaten Earth happens roughly once every few million years, so the odds of one hitting Earth in our lifetimes are astronomically low. Still, the mere possibility of such an event raises fascinating questions about our place in the universe. Are we as vulnerable as we think? Are gamma-ray bursts a ticking clock that humanity must someday face, or are they just another reminder that, in the grand scheme of the cosmos, we are tiny and fragile creatures on an insignificant rock? One intriguing possibility is that gamma-ray bursts have played a role in shaping life on Earth. Some scientists have theorized that such bursts might have been responsible for mass extinctions in the past. The fossil record shows that about 450 million years ago, there was a dramatic spike in the extinction rate, possibly caused by an ancient gamma-ray burst. While this remains speculative, it's worth considering that such cosmic events may have had a profound impact on the evolution of life itself. Perhaps gamma-ray bursts have been the silent architects of Earth's history, shaping the course of life on this planet in ways we are only beginning to understand. And if we expand our thinking beyond Earth, we realize that gamma-ray bursts could be a universal phenomenon. If intelligent life exists elsewhere in the galaxy, or if it has existed in the past, could gamma-ray bursts be part of the reason we've never made contact with alien civilizations? The Fermi Paradox, which asks why we haven't heard from extraterrestrial civilizations, could be explained in part by the deadly consequences of gamma-ray bursts. If advanced civilizations arise near a massive star, they may not survive long enough to send signals or travel to distant worlds. Gamma-ray bursts could be nature's way of keeping the galaxy's civilizations from ever getting too far. A way they could be the ultimate cosmic reset button, wiping the slate clean every few million years and ensuring that no civilization ever becomes too advanced or too widespread. But we must ask, if gamma-ray bursts are such a common feature of the universe, how have we managed to survive this long? The answer perhaps lies in the sheer randomness of it all. While the universe may be filled with deadly stars and unpredictable forces, Earth has found itself in a relatively safe position. The Sun, our life-giving star, is middle-aged and relatively stable. The closest gamma-ray bursts we know of are far enough away to spare us, and while we can never eliminate the risk entirely, our planet is shielded from the worst of these cosmic events by sheer chance. In the end, it all comes down to one simple truth. The universe is dangerous, beautiful, and full of surprises. Ray bursts may one day strike, but until then, we are left to marvel at the forces that govern the cosmos and wonder what lies beyond the horizon of human knowledge. Perhaps, like the stars themselves, we are destined to burn bright, burn fast, and burn out just as the universe intended. As we bring this journey through the cosmos to a close, it's important to pause and reflect on everything we've learned. The universe, with its vastness and unpredictability, holds many secrets, some beautiful, some terrifying. Gamma ray bursts stand as one of the most powerful and enigmatic forces in the universe. We've seen how they can shape the evolution of stars, trigger massive upheavals in the cosmic order, and potentially bring an end to life on Earth in the blink of an eye. But as we've explored, there's more to these bursts than just their destructive power. They're not just a force of nature, they're a window into the workings of the universe itself. These incredible events force us to confront the reality of our place in the cosmos. We're not invincible. Despite all of our advancements, our space missions, our technologies, our understanding of the universe, there are forces far beyond our control. Gamma-ray bursts are a stark reminder that while we've learned so much, we're still just scratching the surface of the vast uncharted mysteries that lie beyond our planet. They're the universe's ultimate weapon, capable of obliterating entire ecosystems, but they also serve a greater purpose. In their wake, they create the very elements that life is built on, and in their destructive chaos, there's a deeper order at play. They are a part of the natural cycle that has allowed life to exist, even as they threaten to take it away. In some strange, paradoxical way, we owe our existence to gamma-ray bursts. Without the violent deaths of massive stars, there would be no heavy elements, no iron, no oxygen, no carbon, the building blocks of life. The elements we are made of were forged in the hearts of dying stars, and it's possible that without these explosions, the universe would be a much quieter, less interesting place. Perhaps in the future, humanity will look back at these bursts, not only as a threat, but as a reminder of the raw power and beauty of the cosmos, the very forces that created us. Yet the ultimate question still lingers in the background. What happens if one of these cosmic weapons were to strike us? What if Earth found itself in the direct path of a gamma-ray burst in our lifetime? The good news is that, while such an event is incredibly rare, it is not entirely impossible. The odds are small, but they're still there. So, what can we do about it? For now, the answer seems to be not much. As we've seen, gamma-ray bursts happen too fast, and their effects are too powerful for us to take direct action. There are no shields we can raise, no weapons we can fire to stop the gamma rays from reaching us. The best we can do is continue to monitor the skies, improve our understanding of these events, and, perhaps most importantly, remain aware of just how fragile our place in the universe is. For all our knowledge, for all our technological prowess, we're still vulnerable to forces far beyond our comprehension. But in the grand scheme of things, isn't that what makes life so precious? It's the knowledge that, despite the dangers, we continue to exist against all odds. It's the understanding that, in a universe filled with the potential for destruction, life, our life, is a rare, beautiful, and fragile gift. Perhaps, in facing the ultimate threats of the cosmos, we're reminded of our own resilience. Just as stars explode and regenerate, just as the universe constantly evolves, so too do we. We rise from the ashes, rebuild, and move forward. We can never predict the future of gamma-ray bursts, but we can appreciate the mysteries they hold. They challenge us to think bigger, to stretch our understanding of the universe, and to ask the questions that truly matter. How fragile are we? What role do we play in the vast cosmic story? What other wonders or dangers are out there, waiting to be discovered? In many ways, gamma-ray bursts are just the beginning of our cosmic exploration. They're a reminder of how much there is left to uncover. As we finish this journey, one thing is certain: the universe will continue to surprise us. With every new discovery, every new insight into the forces that shape our existence, we grow closer to understanding the deeper truths of the cosmos. Whether it's through exploring the origins of gamma-ray bursts, studying the stars, or investigating the unknowns of black holes and dark matter, we are embarking on a journey of endless fascination. And so, as we turn our gaze back to the stars, we can't help but ask ourselves, what else is out there? What other cosmic mysteries lie just beyond our reach, waiting for the next generation of explorers to uncover them? The universe is full of dangers and wonders in equal measure. And while gamma-ray bursts may be one of its most terrifying phenomena, they are also one of its most awe-inspiring. They remind us of the scale of the universe, its power, its unpredictability, and its infinite mysteries. If you enjoyed this cosmic journey, remember, you are not alone in your quest for answers. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you found yourself captivated by the mysteries of the universe, hit subscribe. It's free and it helps us grow this community together. Share your thoughts, your theories, and your excitement in the comments below. Together, we'll continue to unravel the mysteries of the universe. And as always, remember, in the vastness of space, we are all just a whisper away from the next great discovery.